Hi Year 11. So today we're looking at Newton's laws today. So there's 3 laws that we're learning about. And we'll start with our kit quiz, and then you will just need your calculator. There's not as many equations today, you'll be glad to hear. There's just one to learn today. So let's start with our kit quiz. 1 to 5 on your mini whiteboard. Let's pause the video and then come back when you've got your answers for the first 5. Okay, so the first one then, typical walking speed, 1.5 meters per second. Number 2, typical cycling speed, 6 meters per second. Number 3, an object does not return to its original length after it has been stretched, inelastic deformation. Number 4, the point beyond which a spring will be permanently deformed is the limit of proportionality. So it won't go back, it's been stretched too far. And number 5, the area around a magnet in which a magnetic force acts on magnetic objects or other magnets is the magnetic field. So you should have 5 out of 5. We've been doing these key terms a lot, haven't we? Okay, so the title of today's lesson then is Newton's Laws. So a simple title. And he has got 3 laws. So we'll be learning about his first, second and third law today. And for higher tier, we'll also be describing the concept of inertia, which I just find absolutely fascinating. And then we want to recall and apply the equation F equals ma. Quite a simple one today. Higher tier need to explain inertial mass. So we'll work that out today. And then we'll look at some of the large accelerations for everyday road transport and work out the forces involved to move sort of heavy objects. Okay, so that's what we're learning about today. So we'll start with this first law. So this is what you need to start making notes on now. We're going to do his 3 laws, and this is the first one. So if the resultant force acting on an object is 0, so if the difference in the different forces acting on an object is 0, so you've done, say, one minus the other, and it comes out as 0 resultant force, and the object is stationary, then it will remain stationary. So basically, an object that is stationary, you could be sat at your table and you might have a water bottle next to you. If that water bottle is not moving, then it's going to stay not moving. It will remain stationary. If, for example, then you have an object that is moving, it will carry on moving at the same speed and in the same direction. So it'll have the same speed and the same velocity. So when resultant forces are 0 and the forces are balanced, then they keep moving at the same speed, or if they're still and they're at rest or stationary, then they remain stationary, okay? So in the picture of the football, if the football's not been kicked, and the resultant force is at 0, then that ball stays still. And the only time it'll then start to move is if then the forces become unbalanced. So obviously someone kicking the ball, that then changes the resultant force. It's no longer 0, it starts to move, and it will change its speed. But then after a while of being kicked, it will actually, the kind of thrust from the kick will actually balance the air resistance as it's moving through the air, and it will reach a constant speed and direction until then it hits an object, and then the forces again are unbalanced. So again, with a car, you can have a car that's just, say, parked outside your house and it's stationary. And as long as it's stationary, it will stay stationary. And then if you have a moving car and all of the forces acting on the moving car are balanced, so the thrust from the engine is equal to the friction in the tyres and is equal to the air resistance as you move and as you drive, then that car will carry on travelling at a constant speed and a constant velocity. Okay, so this rule is when everything is balanced, when the resultant force is 0, objects that are stationary remain stationary, and objects that are moving carry on moving at a constant speed and a constant velocity. Okay, so that's his first law. Now, I won't play this video in this recording because the sound quality won't come out very well, but can you pause, and then I've put the video link for the Blue Science Guy for Sean in the section on Google Classroom. So you do need to watch it. So it's just a video on Newton's first law. Now then, time to apply that concept to this example. So we've got a spacecraft. It's in outer space, just to put a little bit of detail there, obviously. And when so it's turned off its thrusters, it's broken through the atmosphere, so it doesn't need to overcome the resistive forces of breaking through the atmosphere. So it's now floating. The engines are off, so there's no thrust coming from the engine. And also, there's no friction, there's no frictional forces in space because there's no atmosphere. So there's no sort of bumping of particles along the outside of the spacecraft. So all of the forces acting on this spacecraft are balanced, and it has a resultant force of 0. Now, one of the other forces that would also be 0 at this point is a gravitational force, and it's 0 because you're too far away from the planet and you're too far away from the nearest star. So everything on that spacecraft would be experiencing 0 gravity, so you'd be floating about inside, and that would be exciting. So what have we said so far? So forces are balanced. The resultant force is 0. We have a spacecraft in outer space. It's floating along, and the forces are balanced. There are no frictional forces because there's no atmosphere. There's no gravitational forces because you're too far from Earth and you're too far from the nearest star. So those forces are 0. There's no thrust because the engines are off. So that's 0. So everything is 0. The forces are all balanced. Now, this spacecraft, if it was stationary, it would remain stationary. But if it was moving, then it would carry on moving at that same constant speed. Okay, and this is Newton's first law. So what I want you to do now is I want you to take 4 minutes when you're ready to explain Newton's first law in relation to a spacecraft in outer space. So just like I've done with you, and I've used all these key terms, describe to me, please, Newton's first law. Okay, use all of these words, they should guide you, and take 4 minutes to write that explanation. So pause your video and come back. Okay, so let's see what you've got then. So here's a model answer for what you could have written. So the resultant force acting on a spacecraft in outer space will be 0 if the gravitational and frictional forces acting on it are also 0. And you can see how I took the keywords and I've just underlined them to make sure I use them. And then secondly, then, if the spacecraft is stationary, it will remain stationary. And if the spacecraft is traveling at a constant speed, it will remain traveling at a constant speed. So that is applying Newton's first law. Okay, so you can pause and you can make sure that your answer matches parts of this, making sure we've used all those key terms and that we're marking our work in purple pen. So higher tier now, and although this is higher tier, inertia is just one of those really, really interesting concepts. So this is something that I hope never happens to you. I hope that you're never in a car crash. I really don't want that to happen to any of you. But whenever you have a large deceleration, so you're in a car, you're in a vehicle, or actually you could even be on a roller coaster that suddenly stops, to be honest. You're in a vehicle and then suddenly the driver puts the brakes on. Why does your body keep going forward? So in that picture there, you've got the person with the seatbelt on and the steering wheel. They've put the brakes on and their body keeps going forward even though the car is stopping. And it's because your body has got inertia, okay? So it's the tendency of objects to continue in their state of rest or of uniform motion. So if you're in a moving car, you're moving at the same speed as your car. So if you've got a car traveling along a motorway at 70 miles per hour, your body is also traveling at 70 miles per hour. And that's kind of a weird concept to think about. But when you put the brakes on, you're stopping the car, but you're not stopping you. So you carry on traveling forwards whilst your car is stopping. And the only thing that stops you from going out of the windscreen is your seatbelt, which is why it's important to wear your seatbelt. Now, next time you're in a car, please have a go at pulling the seatbelt gently and does it stop you? And then if you give the seatbelt a really big tug, you'll find that it locks in tight and it stops you going forward. So whenever you're in the car, pull that seatbelt gently and it won't stop you from going forward. But if you suddenly had a very large jolt and you pulled it very, very hard, then that seatbelt stops you going forward, because this is the thing, your body has inertia. And if you're in a car and you stop the car suddenly, it might be that somebody has run out in front of the car, or an animal has run out in front of the car, so you have to slam the brakes on. The car stops, but your body will carry on moving forwards, and that's inertia. And what stops you is your seatbelt. So wear your seatbelt. Now then, I've got a picture here. This is down in Southampton of a man competing in the World's Strongest Man competitions that you may have seen on TV. And he has to pull this bus. And this is always hardest at the very, very beginning. So when the bus is still and he's just starting to pull, it's always the most difficult at the beginning. And so inertial mass is a measure of how difficult it is to change the velocity of an object. So to change the velocity of the bus, when the bus is still, it's got a velocity of 0, and then the man is slowly going to pull that bus along, and the inertial mass is how much mass is needed, to make it change its velocity. So you can imagine this now in terms of something on your table. So again, if you've got your water bottle, imagine you've got 2 water bottles, and one is empty and it has no water in it, and one is full of water. Now, if you then go to push the water bottle, so I happen to have one on my table and it's full of water because I need to get on and drink some. Well, the one that has got water in it is harder to push than the one that is empty. And so the one that's full of water has a higher inertial mass. So it's how difficult it is to change the velocity of an object. So that was higher tier, but it is also just quite interesting. So I hope you've enjoyed that little bit of knowledge. So Newton's second law then is to say that the acceleration of an object is proportional to the force and the mass acting on that object. And we use this equation, F equals ma. So it's one of the easiest equations to remember, along with speed equals distance divided by time that we did the other day. These two, they just happen to be really easy to remember. So F equals ma. And that stands for force equals mass times acceleration. Okay. And generally, when something has more mass, then it requires a greater force to get it to accelerate. And with this equation, then you've got the units newtons for force, kilograms for mass, and then acceleration is meters per second squared. So here's an example to do together. A woman uses the bar to do a pull-up. The woman has a mass of 62 kilograms, so that's our mass. She accelerates at 11 meters per second squared, so that's our A for acceleration. Calculate the resultant force on the woman, use this equation. So we do F equals ma, and we do 62 times by 11, because 62 is her mass. She accelerates at 11, so 62 times 11, and then we work that out as 682 newtons. Now in this question they did give you the unit, but they won't always. So the final answer there was 682. No rearranging, you're just putting the numbers in, relatively simple. Okay, so I want you to have a practice now. What I've done is I've put the triangle up in the corner, because if you need to work out acceleration, you do force divided by mass. If you need to work out mass, you do force divided by acceleration. Remember, when I go through these answers with you, I'm always going to write the equation, put my numbers in, and then work out my final answer with units, okay? So, can you now pause the video and work through the questions? Okay. So here we have the answers then in purple pen. So for the first one, acceleration equals force divided by mass, which equals 25 divided by 65, and a final answer of 0.38 meters per second squared, remembering that the unit for acceleration is meters per second squared. The second one then, to work out force, there's no rearranging this time, it's 14,000 times by 2.5, and you get a final answer of 35,000 newtons. Third question then, so this is our water skier, has a mass of 68 and an acceleration of 1.5 meters per second squared. So 68 times 1.5 equals a force of 102 newtons to move that water skier. And then the last one, the manufacturer gave the following information for a family car. So it's a car that weighs 950 kilograms and accelerates at 3 meters per second squared. Calculate the resultant force. So again, that's F equals ma. 950 times by 3 equals 2,850 newtons. And F equals ma is a relatively simple equation to work with. So it's about remembering F equals ma. Can you then put that into a triangle if that's the method that you like to use, and rearrange it to work out some of the other options? So we're looking for a photo of this. Send us a photo of your equations, all marked in purple pen, and upload those onto Google Classroom. So the third law then, so we've done the first, which was about if they're balanced, then the object remains stationary, and if it's moving at a constant speed, it continues moving at a constant speed. And we've done the second law, where we've said acceleration is proportional to the force and to the mass. Well, this one, his third law, is about when two objects interact, the forces they exert on each other are equal and opposite. So in the picture of the rocket, the thrust from the engine is equal to the air resistance that you experience that would slow the rocket down. So the forces are equal and opposite, and they're acting in opposite directions, but they're equal in magnitude. When the person is pushing on the wall, okay, then the wall is pushing back. Now you think to yourself, well, a wall can't push back, but it does have a reaction force, okay? If they weren't balanced, if they weren't equal and opposite, then the person would go through the wall in sort of a Hulk style. So you push on a wall, the wall pushes back. Then you've got the tug of war. The man is pulling on the rope that's attached to the hook on the wall. And again, you just have to imagine that the wall is pulling back in this one, equal to the pulling force that the man is pulling with, so 500 newtons. And then if you were trying to have a tug of war with an elephant, which I wouldn't recommend, then if the man is pulling with a force of 500 newtons, then the elephant is also pulling with an equal and opposite force of 500 newtons. But remember, they're equal in size, but opposite in terms of direction. Again, another video, but I won't play it because the sound quality on the recording just won't come out very well. So you need to watch that video on one of the links from Google Classroom. And that video was all about Newton's third law, okay? So let's have a look at some of these questions. So figure 1 shows a cyclist with a trailer attached to his bike. Describe how Newton's third law, so it's the one we've just done, applies to the forces between the bike and the trailer. So remember, third law is about having those equal and opposite forces. So same size, pulling in opposite directions or acting in opposite directions. So what would you say for this? It's 2 marks. And then for the mark scheme, we're looking for the fact that the forces are equal in size. So the forces of the bike on the trailer and the trailer on the bike are equal in size. To be honest, if you just wrote that the forces are equal in size, 1 mark. But then you have to say that they're opposite in direction. So the cyclist is pulling to the right, but the load, the trailer, is pulling to the left. So they're acting in opposite directions, and that's the 2nd mark. So you're basically taking the definition and applying it to this example here for 2 marks. Here's another question. A student investigated how the stopping distance of the bike was affected by the mass of the load. So imagine you're cycling along with your load, and we want to see if you put the brakes on the bike, in what distance will you stop? And we'll come on to this concept of stopping distance in tomorrow's lesson. So the same person rode the same bike throughout the investigation. Give 2 other variables which the student should have controlled. So what other things should have been kept the same? Okay, so what 2 other things should have been kept the same? So pause the video, give yourself about 2 minutes or less, and then come back and check your answers. Okay, so here are all the different things you could have said. The same trailer should have been used, the weather conditions should have been the same road surface should have been used, the same gradient roads. So if it was flat, always do flat. If it was hilly, always do hilly. The cyclist should use the same speed. The cyclist should be at the same level of alertness throughout the experiment. So they are not allowed to have a cup of coffee in between the experiment. So there are all the different things you could say. It was a 2-mark question, so we're looking for 2 of these. And it may be good exam technique to have added in a third, because if one of your answers was wrong, then it might be that your third answer was actually correct and would give you 2. So if you need time to write some of these options down, pause the video. And actually, you can pause the video because that is the end of the video. So we've got our last lesson tomorrow then on stopping distances. So we'll be looking at drivers' reaction times and road conditions and various different things. And that's our last lesson for this topic. And then we'll be coming then on to a biology topic next. So that'll be good fun.